underdog. Yeah. And then, like, people won a bunch of money. They had a wind at 52,000 odds against them or something like that. 5,000. I think it was 52,000.
All right, everyone, welcome back.
And that one score to tie it, like, in the last minutes. It's pretty impressive. That reminds me of the pub that we won 20 times.
Can I start? Are y'all ready? Today's the last day, obviously, before our final, which our final is on Tuesday, I believe. Oh, Wednesday, sorry. Our final is on, wait, our final's on Wednesday? Yeah, okay, okay. Our final's on Wednesday. It's at 12:30. I know our class starts at 1. But the final is scheduled at 12:30. They do that for a reason. They offset things. You should not have a conflict with another class final unless you're at a different college somewhere. And we go till 3:15. Okay, on that final, I'm going to talk about the final at the end. I have a guide for you. Okay. So what I'd like to do today is I'd like to start by looking at what I handed you, which, does everyone have a copy of that? Missing one? Are there any extras? For some reason, I said for the copier to print out 25, and I don't think 25 came out. Oh, that's why. Oh, well, the printer messed up, or I messed up. I don't have one. That's it. Yeah, they printed. I got enough copies. They're just printed double-sided. So here's the deal. This is just directly out of the book, almost word for word out of 13.9. It's the theorem in that book, or on the page in 13.9. And I have it. I'll post it up here. I have it right here. So let's see. It's the almighty divergence theorem. It's also known as the Gauss's theorem. And here's what it says. Let E be a simple solid and S be its boundary surface. So we have some three-dimensional solid, okay, sitting here in space, right? Three-dimensional space. We've got some solid here. We're going to call this E. And let S be its boundary surface. So S encloses this entire solid, all right? Let S have positive orientation, meaning that the normal vectors on S, so S is the surface, right? Let the normal vectors be pointing out away from the solid, right? Let F be a vector field. So F is some vector field, P, Q, R, whose component functions, that means the P function, the Q function, the R function, have continuous partial derivatives on an open region that contains E, which basically means that within E, okay, within this solid, those derivatives have to be well behaved, okay, continuous. Meaning when you take derivative, you don't have any problems. No division by zero, no domain issues, okay? As long as that's the case, then if you're trying to find the flux, right? The flux is defined to be the surface integral over the vector field with respect to S, right? That's flux from 13.7, okay? That's flux. That this flux integral converts over to a triple integral over the solid instead of the surface of the div of the field with respect to volume, which is outstanding. In a lot of cases, this theorem makes life a lot easier. All right? You ready to see it in action? Today, I'm not actually going to post homework solutions for this because everything I'm going to do like 4 or 5 examples in class, and that's really like your homework guide, all right? So I'm going to go back. I thought it would be interesting to look at a problem we did in 13.7. Do you remember that? I believe we did that at the beginning of class last time. Does that look familiar? And we were asked to find the flux of this, right? And I timed it. I went back and looked at the video. It took me 17 minutes to do this problem in class. It took me 17 minutes. I'd like to try and do it with this new theorem, if I can. So do we have a solid that is enclosed by some surface S? Yes, we do, right? You can see the solid inside of this. Remember, this is the x-axis, the y-axis, z-axis. So we've got this picture. It's this bowl, right? And we've got the y-axis punching out of it, right? Back here, the x-axis comes out, and z's up here, right? Yes? And this whole thing, this solid E, we have the normals of the surface pointing away from it. And if you go back and look at the work that we did in class last time, that's the way we oriented the surface. And we had to go through and break it up into 2 surfaces and then do surface integrals. All right? But this looks like we can do the theorem. We have a solid. It's enclosed by the surface. Normals are pointed outward. We just got to make sure that the derivatives, right, the derivatives of our vector field are nice. So let's just look at what the div of f would be, because the divergence theorem tells us we're going to need to take a triple integral of the div. What is the div of f? So do you remember how to do div? You do the partial of the first component function with respect to x plus the partial of the second component with respect to y plus the partial of the third component with respect to z, right? And you add them all up. So I would get, what, 0 plus partial of y with respect to y would be 1, plus the partial of z, negative z with respect to z would be -1, and this would be 0. Oh my gosh. Okay, so that means that the surface integral, the flux, right? The flux, according to the divergence theorem, is the triple integral over E of the div of f, which is 0 with respect to volume, and that is 0. And that took me 17 minutes last time, and it just took me about, I don't know, a minute. Yes? That's a great question, all right? The question was, on the final, am I going to tell you which way to do it? Here's what I'm going to do. On the flux problem, I'm going to do a flux over a surface that does not enclose a solid, so you can't use the div. You can't use a divergence theorem, all right? But once you get to a surface, if I ask you to find the flux over a surface that is enclosing a solid, then I would be thinking this, all right? Now, when we did it, we got, like on one surface, I think we got negative pi, and the other surface we got pi, and then they canceled out, we got 0. So it matches up with what we did. It's nice, right? Okay. Done. Now, there was another problem that I did for your homework. Has anyone done the homework for 13.7? Yeah, of course, yes. Of course you have. Okay, that's the homework for this section, but there was a homework problem where you were given, this is from 13.7, number 29 in the homework that I assigned. What they did is they gave you this cube, and the cube was, it had vertices plus or minus 1, plus or minus 1, plus or minus 1. It was a cube. So it's basically centered at the origin, and there were all the corners of the cube landed at every combination of those. So you had something like this. Okay, something like that. I don't know if that makes sense. This is popping out of the center of this side. This is popping out of the center of this side, and this one's popping out of the center of the top. Who watched my video? No? Oh, man, y'all are breaking my heart over here. All right, because I had some trouble drawing it when in my video. Okay, so there's this. This is you were asked in that problem to find the flux, and you were given x, 2y, 3z, and you were asked to find this, okay? And I did it, and what do you think I did when I did the homework for this? I split it up into 6 different surfaces. And then, which formula did I use? Do you think I used a shortcut, or do you think I used the super shortcut that had the normals in it? The super shortcut with the normals, right? Because all of these are flat surfaces. All the normals are nice. So I used that one, and I got through it, and it took me 14 minutes to do it on video. All right? Let's see what happens here now. Does this surface S enclose a solid? Yes? That solid in there is E. So I can convert this over to a triple integral over E. So this is going to become the triple integral over E of the div of F with respect to volume. Now I need to compute the div of F. So what is the div of F here? Do it right here. The div of F is 1 plus derivative of that with respect to y2 plus derivative with respect to z is 6, right? This is 6. All right, that's nice. So I'm just going to do the triple integral over E of 6 dV, right? And I can pull the 6 out, and that becomes triple integral over E of, 6. Triple integral over E of 1 dV. And that just means the volume of E. And what's the volume of this cube? Be a little careful here. This point right here was 1, 1, 1, right? 1, 1, 1. This one down here was 1, 1, negative 1. So the distance between these two is actually 2, not 1. Right? So the side of each side of this cube has a length of 2. Understand? So the volume of this cube is 8. So it's just going to be, where am I? 6 times 8, which is 48. And that's exactly what I got on my video. Isn't that better than breaking it into 6 surfaces? All right, but here's the thing. Divergence theorem is awesome, okay? I'm not going to downplay it. It's a great theorem. But you have to have a surface enclosing a solid. If you don't have that, you throw it out. It's kind of like, you remember when we had line integrals, where we were trying to compute the work on a line integral? We had the fundamental theorem of line integrals. If we didn't have a potential function, then we were just stuck with computing it. But if this curve actually went and came back upon itself, then we had Green's theorem. Because it came back upon itself, we could use Green's theorem. This is kind of the same thing. If you have a surface just floating out there and you want flux, you can't use this theorem. If the surface comes around and closes off on itself and encloses a solid, then you have the theorem. Okay? Do another one. This one won't be as clean, but it will still be better than the way we did it before. So I'm going to bring up, again from last class, after that problem, we did that one. That one look familiar to you? And we broke this one into 4 surfaces. It was the front side, it was the back side, it was the bottom, and it was this top piece, right? And I'll remind you what each of these were. I'll just put them up here. This front surface was x is 2. That's not a 2. That's a 0. x is 2. This back side was x was 0. The bottom of this thing was z was 0. And then this came from z equals square root of 1 minus y squared, where y was between negative 1 and 1. So you can go back and look. We talked about this last time. All right, so I'm trying to find the flux. I want to know this, right? So am I allowed to use the divergence theorem? Yes, because this surface S is all of those surfaces together and closes a solid, right? And so I'm going to need to compute the div. So let me get the div. This is going to be equal to the triple integral over E of the div of f dv, but the div of f, not as clean as the other ones we've had, right? What is it? 2x plus 2y plus 2z, right? Okay, well, it's not a constant, but it is what it is, right? So now this becomes the triple integral over E of 2x plus 2y plus 2z dv. And now we're back in chapter 12. It's just a triple integral, right? And you just need to come up with some way of controlling x, y, and z so that you can draw that region for me, that solid. So does anyone have an idea of how you could do that? Go to cylindrical coordinates or polar coordinates, right? Now what I'd like to do is I'd like to project this image onto the YZ plane, okay? Just so you can have an idea of what it looks like in the YZ plane. It's going to be the top half of this circle, right? That's a projection on the YZ plane. So I should be able to look at the Y and Z and look at this region as in cylindrical or in polar, right? The only other thing for me to figure out is what about x? Well, x is what? 0 to 2, right? So that should be easy to control, x between 0 and 2, and I'm done. It's just a matter of converting this region over because it's not a type 1 or a type 2. It's more of a polar region. So you all with me? So I'm going to go ahead and make my conversions now. I'm going to let y be equal to something and z be equal to something. What am I going to let them equal?
Y is going to be
R cosine theta, and this is sine theta, right? And then we have the Pythagorean identity, you know, y squared plus z squared is r squared. All those things are in play, right? And I'm going to put my restrictions. What are my restrictions on theta? What are my restrictions on r? And what are my restrictions on x? Because those take care of the three variables, right? So theta is between 0 and pi, because I don't want to draw the whole circle. I just want to draw the top half. And r is between, it was 1 if you go back and look at last class. This was 1 and that was negative 1, so r is between 0 and 1. And then x is between backside and front side 0 and 2. You all okay with that? All right. So I'm just going to rewrite this triple integral. I'm going to rewrite it with those variables. So it's going to become triple integral. I'm going to put my limits of integration on here in just a second. 2 times x is just, well, can I pull a 2 out of everything? Okay, 2. X by itself is, well, it's one of our variables, so just x. The y by itself, what was y? R cosine theta. And then plus, what was z? R sine theta. All times r, because we did do a conversion, right? Cylindrical is polar, so I have to put an r. And then I have, what, d theta, dr, dx. I can go in any order I want. I'm just going to go dr, d theta, dx. And then I'll put my limits. I'll start from the outside in. X's go from 0 to 2. Theta goes from 0 to pi. And r goes from 0 to 1. Good? I'm going to take this all the way. This is equal to 2 times the triple integral 0 to 2, 0 to pi, 0 to 1 of xr plus r squared cosine theta plus r squared sine theta dr d theta dx. So I just distributed the r through. And now I'm going to integrate everything with respect to r. I don't think I need this picture anymore. I need the space, though. Equal to 2 integral